Welcome to E-Padasala PG program for computer science students. Today we will be looking at scheduling policies with RTOS. In this module, first we will be looking about the priority based scheduling. In that priority based scheduling, we will be looking at static priority as well as dynamic priority algorithms such as rate-monotonic scheduling and earliest deadline first scheduling. RMS and EDF scheduling we will be discussing, and we will be at the end we will be discussing about inter-process communication. So, in this embedded systems we are having real time operating system. So, in the previous models we have discussed about the need for priority based scheduling in the embedded system products. So, the real time system, if efficient, when you are looking at priority based scheduling is adopted for embedded system development. I mean any product which requires the task should be scheduled properly as well as the CPU should be utilized efficiently, then that product will be working very well. So, if I am looking at that particular aspect, RTOS is looking at the priority based scheduling. So, in this model we will be looking at the priority based scheduling. So, we know very well the OS kernel determines what process to be executed next. So, for each task when you are looking at priorities, we will be giving a numerical priority which is assigned to each task. So, the kernel can simply look at the process and their priorities. It see which one is actually want to execute and select that highest priority process that is ready to run. So, at the same time so many processes may be ready, but the RTOS will schedule the process which is having the highest priority. So, that is the basic behind the priority based scheduling. So, here the mechanism is very flexible and fast. So, when you are looking at priority driven scheduling, each process has a fixed priority that does not vary during the course of execution. So, the ready process with the highest priority is selected for execution always. So, a process continues execution until it completes or it is preempted by another higher priority process. For example, when you are looking at there is a table which has been shown over here. So, in this table we have three processes, one is P1, another one is P2 and P3, where P1 is given a topmost priority, P2 is given the next top priority and P3 is the least priority things, and it takes the execution time like 10, 30 and 20. So, if I am having a work is having one particular system will have three different tasks or three different processes P1, P2 and P3, and each has a different priority and different execution time. So, if this is the scenario, we will see that how the scheduling schedules the things based on the priority. So, when you are looking at this, the P2 is first ready to run when the system is started. The P1 is released when at the ready state, when the start of the time the P2 is ready. So, it has been released. So, this has been scheduled, the P2 is being scheduled for running the process. Remember, P1 is having a higher priority than your P2 and P3 is having a least priority than this particular P2. So, if this is the case, when it is executing, suddenly at 15th time at 15th time unit, the P1 is getting released. So, now this P1 is having a topmost priority, because of that it preempts this P2 process. So, now this has been preempted by P1 and P1 is scheduled. So, because it is a highest priority job, nobody can preempt this particular service. So, the P1 is continued and it is executing completely without having any interruption. So, just look at over here, at a time of around 18 P3 is released. At 15 it started working, but at 18 P3 is getting released. But remember, P1 is having the topmost priority, because of that though the P3 is ready, the P1 is continued doing its job. I mean it has been allowed to do that particular task only, P1 only. So, P1 is executed completely. After that, when you are looking at the P3 is, though the P3 is released, already P2 is preempted by P1. Because of that, we will be looking at P2 and P3. P2 is having the next good priority, I mean high priority. So, P2 is scheduled. So once P2 is finished, then only the P3 is taken and it has been scheduled. So this is the way task will be scheduled when you are looking at the process 1, process 2 and process 3 having a different priorities, and the RTOS schedules like this way only. Taking into consideration this kind of scheduling, we have one particular problem. One is this priority inversion. So when the priority inversion takes place, that we have to consider. So always in real time the priority inversion problem will occur, and if I am looking at the task 1 has a highest priority than task 2, also the task 2 has higher priority than task 3, and there is a mutual exclusion is used in accessing a shared resource. So priority inversion may occur when you are looking at the shared resources. So when we are thinking that there is a resource will be shared by 2 processes and the higher priority task is asking for the service, by the time the lower priority task is holding the resource, then there will be a problem. So this problem can be avoided, or it can be solved by certain remedial measures. So one is we can correct the problem by raising the priority of the lowest, I mean the task 3. That means that the task 3 is having a lower priority but it holds the resource. So when you are looking at the task 3 is executing with particular resource, then we will be making that that particular task should have a highest priority. So just for a time it accesses the shared resource. So by the time we will be allotting a high priority to that particular task. After that, return the original priority. That means once that particular task is over, then you have to resume the original priority to that particular task 3. So if the task 3 finishes the access before being preempted by task 1, then what will be the problem? Then what will happen, and how we will be looking at that particular situation. So the better solution is the priority inversion problem. Actually when you are looking at the better solution to priority inversion problem is priority inheritance. So what we are trying to say over here is automatically we have to change the task priority when it is needed. For example, if somebody is accessing resource, then we will be thinking that that resource will be asked by some other process also, maybe that is the highest priority task. So what we will do it irrespective of what is the task which is holding the resource, we have to increase that the priority of that particular task. For the time being it has to hold that, for the time being, that means until it has to finish that particular work with that particular resource. So if we are doing that way, then this problem can be avoided. So when you are looking at this kind of priority assignments and priority inversions and the problems due to those things, we have to know that what way I can solve these problems. So first we have to see that how the different type of methodologies are used in case of priority based scheduling. So the first one is static priorities with the scheduling, another one is dynamic priority. So when you are looking at static priority, the name itself shows that once we have fixed the priority of each and every task before starting that particular execution, then it has to be retained till the whole process is getting over. The example is RMS scheduling, rate-monotonic scheduling. The next one is the dynamic priority. The name itself says that the priority is dynamically changing when you are running the process. So no task is having the highest priority. The priority of the task is getting changed each and every instant based on the current scenario. So that is nothing but dynamic priority. So in this, the one of the example is the earliest deadline first algorithm, which is otherwise called EDF algorithm. So when you are looking at the RMS scheduling, in this, scheduling policies developed for the real-time systems only. So it is a static scheduling policy. So the fixed priorities are sufficient to efficiently schedule the processes in many situations. So here the theory behind this RMS is all processes run periodically on a single CPU, and the context switching between the process, the context switching time is ignored. So these are the two things we will be making it as assumption. That means the context switching time is ignored and all the processes are running periodically with single CPU. The next thing we will be assuming is there is no data dependencies between the process, and the execution time for a process is always constant. but it never happens in a real time. But anyway, we will be looking at the process execution time is always constant. All deadlines are at the ends of their periods. So, each and every process has their own period. We will fix their deadline as the end of their period. The highest priority ready process is always selected for execution, and the priorities are assigned by rank order of the period, that is the process with the shortest period being assigned the highest priority. It provides the highest CPU utilization while ensuring that all processes meet their deadlines. So, when you are looking at RMS scheduling, this is an example where P1 is given the topmost priority, P2 is given the second priority, P3 is given the least priority. So, if this is the case, first we will assume that all the three processes are ready at the initial stage. So, by the time the P1 is getting started, so once it is getting started, it is allowed to continue its execution because it is having a high priority, nobody will preempt this. So, you just look at over this particular scheduling, you will find out that each and every period starting, that means for your P1 at this period is over by 4. So, for the next period at 4 itself it starts execution, because nobody will preempt this. So, he will be given the first priority. So, because of that, each and every time when it starts the period, this has been getting scheduled. So, at 0, 4 and 8 it starts. So, when once this is over, he has to be given the highest priority. So, the P2 is given the next priority. So, because of that, P2 is getting scheduled, and he will be scheduled from at the time slot when P1 finishes. So, from there onwards it is allowed to execute for 2 cycles. So, then if the P1 is not started its next period, then only the P3 is allowed to execute. So, P3 when it started executing it, when it has 3 periods to execution time, but it has done only 1 period. So, by the time the P1 is getting the next period, because of that it preempts P3 and it started working. So, once this is over, because the next period of P2 is starting at after 6 only it has to start, it has been over by 5 only. So, 5 to 6, that means 1 clock cycle P3 is allowed to execute. Once it has done only 2 cycles execution, so by the time the 6th period has come, so the P2 is getting a topmost priority. So, because of that it preempts this and it is allowed to execute. So, just look at over there, these persons when their period is over and the next period starts, they will be ready, they are allowed to execute complete their work when you are compared with this kind of the least priority task. So, these things are, I mean P3 is preempted 2 times and it is over by only 10. But anyway, this has to be over by only at least by 12 clock cycles. So, this happened within this 12 clock cycle. So, there is no problem in this particular scheduling. So, in this scheduling, when you are looking at the different set of times, we have to see that how the process has been executed, and within the full hyper period all the tasks are scheduled or not, that also we have to be very careful. So, when you are looking at this is an process table, you just see that there is actually the period is 12 cycles, maximum is P3 is having a period of 12 cycles. When you are looking at P2, it is having a period of 6 and P1 is having a period of 4. When you are scheduling it with P1 as high priority, P2 as second priority and P3 as third priority, by looking at based on the priority wise, P1 is executed, when you are looking at the P1 is executed 3 times and P2 is executed 2 times, and when you are looking at P3 has to be executed at least by 1 time. So, if that is the case, you just see that 3 into 2 is 6, this is 3 into 2 is 6, so 6 plus 6 and this is 3. So, when you are adding up all these things, I will be getting a time unit of 15, but you just see that P3 has to be ended before 12. So, the deadline is missed when you are looking at your P3, though it looks like 4, 6 and 12 is their periods, it looks like it can be scheduled very easily because the overall time slot required for doing at least one time is something like 8 only, 3 plus 3 plus 2 is 8. So, when you are looking at 8 with 12, we will think that the process can be scheduled properly so that we will not miss the deadlines. but actually when you are looking at the scheduling with priorities, we will miss the deadline. That is what we are trying to say. So when you are looking at the utilization of this kind of scheduling is, we will be looking at, this is an example, T1, 4 is the period, 1 is execution time, 5 is a period, 1 is execution time, T3, 10 is a period, 1 is the execution time. So then the sigma ui is equal to 1 by 4 plus 1 by 5 plus 1 by 10, which is 0.55. That means it should be less than or equal to 1. The 100% utilization is there or not. We have utilized half of the slightly higher than the half of the CPU cycle to schedule these tasks. So you just see that sigma ui should be always less than or equal to n to the power of 2 1 by n minus 1. If it satisfies this particular rule, definitely we will say that it can be scheduled with RMS algorithm. So here you just see that 3 2 power 1 by 3 minus 1, which is approximated to 0.78. So 0.55 is always less than 0.78. So it can be schedulable with RMS scheduling. That is what it says, that when any of the task is given, we can look at this particular formula and we will see that, we will assure that this can be scheduled, this task can be scheduled with RMS. Sometimes this rule may fail, but it may be scheduled. That case also will happen, but that is very rare case. So you just look at over here, but this is, if it obeys this particular rule, that kind of set of tasks can be definitely scheduled through RMS. So that is what we are trying to say with this according to this particular paper. So this is actually this RMS utilization bound, which says that the number of tasks as well as the utilization, you just see that 0.78, 0.55 is the number, 0.78 is the utilization thing we will be looking at. So the maximum is 1. So that way you have to see that 100% utilization can be obtained through this particular one. The number of tasks, when you are increasing it, it goes this way only. The maximum is 0.78. So when you are looking at, as I told you, the deadline miss is the great problem with respect to rate monotonic scheduling. So here this is a case where you just see that the time is 1, 4, task 1, task 2, 2, 3, 2, 6 and task 4 is 3, 8. So if this is the case, you just see that 1 by 4, 2 by 6 and 3 by 8, which is equal to 23 by 24, which is less than 1 only, but still when you are scheduling it with your RMS, you just see that because T1 is given the topmost priority, each and every period starts, it gets executed, and the next priority is T2, so because of that each time when it is over, it gets executed. So when you are looking at, because the next period is here, so it has been scheduled here and here, and this will be happening for this. When you are looking at the deadline is over, by the time it has done only 2 clock cycles, one of the clock cycle is executed after this particular deadline. That means after 8, even 9 also it can't, only at 9 only it will be in a position to give it. So if this is the case, though it looks like 23 by 24 is less than 1, but because of the priorities are fixed and the top priority is preempting the lower priorities, we misses the deadlines. So this has to be rectified. Because of that, people went through EDF scheduling. So when you are looking at EDF scheduling, which is nothing but a dynamic priority algorithm, that means the priority is fixed dynamically while you are running the tasks. So in this actually, first thing is the dynamic priority algorithm, the highest priority job is fixed only with its deadline only. That means the highest priority job is the one with the earliest deadline. So if I have 4 or 5, each and every instant we will be fixing up priority based on the deadline. So we will be given the top priority if that particular task is getting a earliest deadline. So that is the basic idea behind this EDF scheduling. So in dynamic priority algorithm, the priority of the task can change during its execution based on the initiation time. And the fixed priority algorithms are subclass of more general class of dynamic priority algorithms. So the priority of a task does not change with respect to fixed priority. The dynamic priority algorithms, where the priority of the task is changed each and every time inside while it is running. So when you are looking at dynamic priority algorithm, the priority of a job is inversely proportional to its deadline. and when you are looking at the lowest priority process, which is the one whose deadline is furthest away, that means that will have a longer way to go for its deadline, then they will be, that particular process is given the lowest priority. So the priorities must be recalculated at every completion of process. So the final procedure is but the same as the allotment of the process is, the scheduling is done with the same kind of procedure as RM, only the priority is changed based on this particular algorithm. Just look at, this is an example where we have a T1, process 1 has execution time as 1 and the deadline as 4. Process 2, it has a execution time as 2 and deadline as 6, and T3 we will be having a value of something like 3 to 8. So when you are looking at this process, you will be just see that T1 is scheduled first, because see, when you are looking at always the task, we have to first find out the utilization ratio. So you just see that the same task which we have found that which cannot be done through RM has been taken for an example to schedule it with your EDF. Just see that the same thing where we will be getting utilization ratio as 23/24, which is less than 1. So if I am finding it is less than 1, then I will say that it can be schedulable with EDF. So when I am looking at this, first I will be looking at this is 4 and this is a 6 and this is 8. So because of that, T1 is given the topmost priority. So it has been scheduled first. This was over. So now you just look at these two things. These two things, when you are looking at, this is getting over by before. So this is given the next priority. So this has been scheduled. So once this is over, I will be looking at which is the next deadline schedule. So this is the next period schedule for the task 1. For the P2 it is the next schedule. For P3 it is the next schedule. So we will see that when you are looking at, these two are of the similar place and this is far more away. But when you are looking at these two are at the same place, but this has been scheduled 2 times, it has not been scheduled, this has been scheduled at least 1 time, this was not yet scheduled. So because of that, we'll take one particular policy, we'll assign this particular one. So if that is the case, this has been scheduled for the next process. So this is over and this is over. Now when you are looking at this is a deadline and this is a deadline. So because of this is having a highest priority now, this has been scheduled. So T1 is scheduled. Once this is over, when I am looking at these two are the things next when you are looking at the earliest deadlines. So if that, because this period is over by only this clock cycle, so we will be looking at either this process or this process has to be run. So if that is the case, when I am looking at over here P2, because this process is not at all getting over, this period is not at over and this period is still has to be completed, this also has to be completed. So I will be looking at this and this only, because this has been, this period will not be considering it because it starts at this particular period only. So we will be looking at P2 has to be scheduled next. So P2 is scheduled completely. After that we will be looking at both are having this same schedule. So because and this period is started, so it has been assigned. So when you are looking at the next schedule, 1, 2, 3 are the deadlines, but this has been scheduled many times and it has been scheduled only 1 time. So this has been given the priority and it has been scheduled, and after that this has been scheduled. Then when you are looking at the the deadlines, this and this gets scheduled. So that is the way when you are looking at your EDF scheduling, each and every time we will be looking at who will be reaching the deadline first, then I will be giving the topmost priority to him. So based on that I have scheduled it. So if this is the case, you just see that here the same scenario with the 3 tasks with the same execution time and deadlines, we will be in a position to schedule it within the particular time limit. There is no overload, deadline miss with respect to this particular EDF scheduling. So this is an example 2 where just see that 1, 4 and 2, 5 and 2, 7 are the things. You just see that when you are looking at these deadlines, we will be having something like these, this are the 3 things which will be having it. It is at the earlier stage, so this has been scheduled, next is scheduled by this, and when you are looking at this, this will be scheduled next. So when you are looking at this and this scheduled first and this scheduled next and this scheduled this way. So it's a very simple scheduling based on looking at only the deadlines, and based on that it has been scheduled in a proper way with respect to EDF. But still with the EDF we will be having a problem just like overloading. That means you just see that we have T1, T2, T3, T4 are the process, but when you are summing up this 3 plus 3 plus 3 plus 3, so 12, but you just see that all the persons who will be having the deadlines maximum of 7. So 12 has to be finished within 7 means definitely this will not be possible. So there will be a deadline miss for all these tasks. So because of that we will be getting a domino effect with respect to EDF. We can schedule it, but still when you are looking at this, some of the process will get processed properly, some of the process will miss its deadline. So this may be the third example with the EDF. You can just do it this way also. So now when you are looking at RMS versus EDF, RMS is a simpler implementation even in systems without explicit support for timing constraints, and predictability for the highest priority tasks is also easy. But when you are looking at EDF, the full processor is utilized, complete the CPU utilization is very good, but the misbehavior during the overload conditions will occur, and we can't predict it before itself, because the schedule, I mean the priority is decided only at the time of execution. So based on that we can't predict it earlier itself who will be finishing off first and other things. So that was the difference between your RMS and EDF. So the next is inter-process communication mechanisms. So when you are looking at the different processes are there, how I will be communicating with each other. So that is very important. So when you are looking at this kind of communications, first one is shared memory communication, another one is, I mean when you are looking at messaging. So when you are looking at shared memory communication, there I will be having, you just treat CPU is one process and IO device is another one process. These two persons wants to communicate with each other. What they will be doing it is, there is a shared memory over there. The CPU wants to send a data to IO device, this will put it over there in this particular memory, and whenever it is free it comes and read it from there. Only thing is the IO device should know that what is the starting location at which the CPU writes the things. So and when the IO device wants to give the input device wants to give the data to CPU, then it will just put it in this particular memory. CPU when it is free it comes and reads it. So the shared memory is used by the task so that nobody can wait for each other. This is one kind of communication which is otherwise called a non-blocking communication. So when you are looking at another one communication is message passing, where we have one particular task where there will, I mean whoever be the sender or receiver, there they will have a buffer which is otherwise that particular one is used for receiving or sending the data. For example, if the CPU wants to send a data to CPU 2, it will go over there and it will write whatever be the content it wants to send it to CPU 2, so that it reads from here. So the same way when he wants to send a data, he will put it over there, he will read it. So now you just see that the data is written on to the devices, not on the communication link. So when you are comparing with inter-process communication in the shared memory concept, there the data is stored in the communication link itself, but here the data is stored in the receiver and sender itself. There the message is written and it has been read. So when you are looking at the Unix based processors where the inter-process communication is done through the signaling. So the signals are analogous to interrupt, but it is a software created one. So the signal generated by a process and it will be transmitted to another process by OS itself. So the processes will communicate with each other through different mechanisms. One is blocking, another one is non-blocking, where the blocking kind of communication is nothing but, I mean non-blocking is nothing but they will not wait for each other to say yes or no, it will send like your shared memory. When you are looking at blocking, there if I wanted to send a data, I have to ask him, he has to say that, just like handshaking, it has to say that I am ready, you send it, then only he can send it. So that kind of communication is used when you are looking at your inter-process communications. So in this model we have discussed about priority based scheduling. In that also we have discussed the RMS, which is a fixed priority scheduling, and EDF, which is otherwise called it as a dynamic priority based scheduling. And at the end we have discussed about the inter-process communication. Thank you.